Hey guys, today we'll be talking about the Einstein field equations. Now, the Einstein field equations are a set of mathematical equations that describe the curvature of what we call a space-time. And this phenomenon, this effect, is what causes what we know as gravity. So, Einstein in 1915 discovered that if I have two objects of mass, that these objects aren't actually being attracted to each other. Einstein discovered that the reason why two objects of mass will accelerate towards each other is actually because they curve something called space-time. They would both curve space-time, causing each other to accelerate towards the other. Now, this is a simplified depiction of what Einstein discovered, but we're not going to get into the details in this video. In this video, we will just motivate the Einstein field equations that describe this curvature of space-time, and we'll talk about what space-time really is. Now, these equations with an S are called the Einstein field equations. The reason why I say equation with an S is because these are really 16 sets of equations. It's just being compacted into one. Because these symbols over here, these mu's over here, are just indices. And mu and nu can have values for 1, 2, 3, and 4. So basically what I'm saying is you would have a solution, not a solution, but these equations are really 16 equations that are being represented into one equation. And let me give you a better example of that. So I have a set where mu equals 1 and nu equals 1, which would look like this. I can have a set where mu equals 1 and nu equals 2. And the equation would look like this over here. It would look like this. I can also have a solution where not all of the mu's are 1, and not all of the nu's are 1. I can have a set that looks like this. And this would be 2. This could be 2, 1 instead, and so on. So when we can write out these equations as 16 separate equations where there is a different value for mu and nu, and mu and nu both go to number 4. And so this is really kind of a summation. And the summation that we call this summation, the name for it, is called the Einstein summation convention. And we're going to learn about that more in the future. So now that I've told you the form that this formula is presented in, let us talk about what each of the components mean. I have it written of what each component. I have written the name for each component. This component over here is called the Ricci tensor component. This component over here is the Ricci scalar curvature. This over here is the metric tensor component. Here is the cosmological constant. Say that 10 times fast. And here, this component is called the stress energy tensor. And in this video, we're gonna give a brief intro to each of these components. And we will start with the Ricci tensor component. What is the Ricci tensor? And what is a tensor in the first place? Well, a tensor, for this video, will be a mathematical quantity that is invariant. And this invariant, what does this word mean? Well, invariant, something is invariant when it doesn't change under a change of coordinates. So a tensor is going to be a mathematical quantity that doesn't change when you change your coordinate system. So let's say I have a Cartesian coordinate system that looks like this. If I have some tensor, if I have a mathematical object in this coordinate system, and if I change that system into something like this, let's call it the squiggly line coordinate system, the tensor remains unchanged. It's still the same. So, for example, the number 5 would be a tensor. If I have 5 apples, if I drew 5 apples, 1, 2, let's copy and paste that. If I had 5 apples under a grid, and then I change that grid, if I change that grid into something like this, like a Spider-Man grid, kind of, there are still 5 apples. The apples didn't change quantity. So the number 5 would be a tensor because it is invariant when I change the coordinate system that I am using. There are other types of cool tensors that we will be talking about in the future. Well, actually, we're going to talk about the cool tensors right now. So the Ricci tensor, represented with R mu nu, is, well, the actual tensor is represented with the letter R. And R mu nu is just showing the tensor in its component form. Here is the actual tensor itself. Don't confuse this R with this R right over here. There are two different things. It's kind of dumb how Einstein used the same letter, but that's what we have. So this R is the tensor form for the Ricci tensor. The R mu nu is the component form. So it turns out that we can represent tensors as things called matrices. Like I can represent the number 5 as 5 in a matrix, pretty much in a bracket, and the component would be 5. 5 is the component. If I have a matrix A, where A equals 1, 2, 3, 2, 5, 0 for the matrix, the 1, 2, 3, 2, 5, 0, those are the components. Okay, those are the components. And I can represent this matrix abstractly with the components A, 1, 1, A, 1, 2, A, 1, 3, and A, 1, 1, not 1, 1, sorry, and A, and A, 2, 1, A, 2, 2, and A, 2, 3. And these A values are the components. In this case A11 equals 1, A12 equals 2, and then so on. You get the point. It's trivial. So this R mu nu is the Ricci tensor in its component form. Just like how this A11, A12, and A13 is the component form for A. And we can just say A mu nu. Or mu can be 1 and 2. 1 or 2, and nu can be 1 or 2 as well. So really, A mu nu is the component form for A. These values are just particular values for mu and nu. So that's what the Ricci tensor component is. Or that's what a component means. That's what a component represents. Now it turns out that we can't represent the Riemann curvature, we can't represent the Ricci tensor as a matrix. At least not to my knowledge, we can't do that. So that's why we tend to stick with the component form for the Ricci tensor. Now, what is the actual geometric meaning of the Ricci tensor? Because 5 is a tensor, and 5 apples has an actual geometric meaning. There's 5 apples. So what does the Ricci tensor physically mean? Well, if I have some space, like a sphere, for example, or a basketball, if I had some sphere, excuse my terrible artistic skills, but if I had some sphere and I had a vector attached to it, if I were to move this vector around in this closed loop, it turns out that for the vector to stay on the sphere, the vector would need to change its direction. Try it yourself. Take a vector and make the vector tangent to the sphere. For the vector to remain tangent to that sphere, the vector needs to change its direction. It's kind of like how you can have the Earth. Have a drawing of the Earth with all the continents and stuff. Just a quick drawing of the Earth. Saudi Arabia. Then here's Africa. This is pretty bad. I kind of messed it up. But if this is the Earth, and I have all these clouds and stuff, this is the Earth's view from space, and I had some stick figure on the Earth, and he had a vector pointing out from his head. If the stick figure were to stay on the Earth and walk around the Earth, like over here, the vector on his head would change its orientation. Let's compare these two vectors. As you can see, there is a change in these vectors. There's a separation vector. Keep that in mind. Now the Ricci tensor, not Ricci tensor, but the Riemann curvature tensor. There is something called the Riemann curvature tensor, represented with an R. In its component form, the Riemann curvature tensor is represented with these indices, I, J, K, L. Now the Riemann curvature tensor acts on two vectors being paired together, and then another vector, and it returns the separation vector, which we would call K. So if I had a loop formed by V and A, and I had some arbitrary vector and transported it along this loop, this vector might look like this. Well, W would represent the vector being transported, and then K would represent the separation vector between the initial W vector and the new W vector. So we can call this W prime after being transported along the closed loop, and then K would be the separation vector between W and W prime. We can zoom in right there. So R would be something called the Riemann curvature tensor, and that's what it does. Now the Ricci tensor, which is also represented with an R, is the contracted form of the Riemann curvature tensor. Keep in mind the component form is R mu nu for the Ricci tensor, and the Riemann curvature tensor, its component form is I, J, K, L. So, and it turns out that we get the Ricci tensor, we get that tensor by contracting the Riemann curvature, by contracting the components of the Riemann curvature tensor. Now, what's a contraction? Well, we contract the tensor by multiplying it by something called the metric tensor. So I might have, we multiply it by the metric tensor to contract it. Now, don't get too tied up in this. I haven't explained what the metric tensor even is, and I'm not even sure if I use the correct indices or the correct normal form of the tensor. So basically, we contract the tensor by multiplying it by some value called the metric tensor, which we also see in this equation over here. Now, so I talked about the geometric meaning of a Riemann curvature tensor. What about the Ricci curvature tensor? Well, the Ricci curvature tensor, also represented with R. Einstein loved his R's. The Ricci tensor, it tells you about how volumes change in space. Let's take that same drawing of Earth, because I kind of like it. Let's take the same drawing of Earth, put it over here, remove this, remove all the people. Now, what is the straightest possible path on Earth? What if I had a person over here on the North Pole, and let's say I tried to walk as straight as possible to Abuja, Nigeria. Okay? What is the straightest possible path? What would that look like? Would that be a line? No. As the surface of the Earth is curved, the straightest path along that surface, in that surface, would be a curve. That might look like this. And let's say I wanted to instead go to Sacramento, California. So I wanted to go to Sacramento, California, in the USA. My path might look like this. That would be the straightest possible path in the curved space. Now, there's a special name for these paths, and they're called geodesics. Geodesics are the straightest possible paths in a curved space. It's the path. It's the shortest distance. I don't want to say that, because it turns out that geodesics could also be the longest distance. But the geodesics are the paths that are the straightest possible paths in a curved space, which would also be the shortest distance between 2 points. So the shortest distance between 2 points will always be a geodesic. But that doesn't mean that all geodesics are the straightest possible distances between 2 points. Okay. In a flat plane, geodesics are just straight lines. The straightest possible path in a flat plane is just a line that connects from point A to B. And we can do geometry on this plane. And since the plane is a flat plane, we call the geometry Euclidean. In a curved space, the geometry that we do on a curved space is called non-Euclidean. Does that mean if I start measuring stuff on Earth, measuring distances on Earth, does that mean I'm doing non-Euclidean geometry? Not necessarily. On short patches of Earth, like your house, the geometry is mostly flat, so we can do perfectly Euclidean geometry with only little error. But if you look on global patches of the Earth, like this whole patch over here, if I'm doing Euclidean geometry to build a bridge, I'm gonna get some terrible. I'm gonna get a terrible model of the bridge. It's kind of like how we can't use flat maps that when navigating around the Earth, if that flat map doesn't account for distortion. So I haven't explained what the Ricci tensor was. I went off on a tangent. So the Ricci tensor, it basically says if I have two geodesics. Okay, let's just delete this whole thing. The Ricci tensor basically says that it basically says as now if I have two geodesics on any plane, not on any plane, on any space, on any surface, let's just make that, yeah, then I can draw a shape. Okay, that was worded terribly. Okay, so let's say I have two geodesics. I can draw any shape from the endpoints of the geodesics. I could draw any shape from the endpoint. And as you can see here, these geodesics eventually will meet. as you can see, the shape that we formed shrinks as they travel along the geodesic. And the Ricci tensor will measure the rate of change of these shapes. It will track how these shapes would change along the geodesic. For a flat plane, if I had two geodesics, aka straight lines for this plane, and I had some shapes, the Ricci tensor would track how these shapes. It would track how the area or the volume of these shapes would change as they travel along my geodesics. And yeah, that's what it is. It helps you find that. I haven't talked about the actual how the math will show that, because this video isn't going to be that rigorous, just descriptive but not rigorous. So a cool side note is that we can actually find we can actually find what our geodesics would look like for any surface by using something called the geodesic equation. And we will actually be solving that for some shapes in the future. So our next tensor is this 1/2. What does 1/2 mean? Well, 1/2 is actually equal to your IQ. Okay, so our next tensor from that one will be the metric tensor. What is that? That's actually my personal favorite tensor. I love to work with it. The metric tensor tells you about just distances across your space. If I had 2 points, well, how would I find the distance between these 2 points? Well, you might just say, oh, it's obvious. We just use the Pythagorean theorem. Just do this and this. We just use a squared plus b squared equals c squared, blah, blah, blah. Well, it turns out that's wrong. You can only do that when your space is flat and Cartesian. So it only works in one special case. The general formula for distances uses the metric tensor. The metric tensor acts on a vector twice and gives you the distance between those two vectors. No, sorry, it gives you the distance, or aka the length of that vector. Now, the metric tensor also measures the dot product. Wait. I made a mistake. The square roots of the metric tensor acting on the same vector twice gives you the length of a vector. Now, if I have the metric tensor acting on two different vectors, v and w, it gives me the dot product between those two vectors. The metric tensor is actually pretty simple to explain and simple to calculate, unless we are dealing with pseudo-Riemannian four-dimensional geometry of space-time. So the metric tensor is quite simple in normal cases in math, but when talking about general relativity, we cannot actually find the metric tensor simply. We have to solve the Einstein field equations. In fact, the metric tensor is really important in this subject, because when we solve for the Einstein field equations, what are we actually solving for? Oops, scrolled a tad bit too far. When we are solving the Einstein field equations, we are actually solving for what this is. It's that important. When we solve the equations, we actually solve for what your metric tensor is. Why is that? Because everything you see here, this over here, well, everything you see on the left side, besides these constants, this and this depends on your metric tensor. Your metric tensor, G, kind of, it physically describes the geometry of your space. Your metric tensor will determine the rate of change of your coordinates. It will tell you the specific geodesics that will exist in your space. It will tell you your Riemann curvature tensor. It will tell you your Ricci tensor. It basically tells you everything about your geometry. All geometry, I might even say all geometry that you can do on your space will depend on your metric tensor, which is why the metric tensor is such an important tensor in not just differential geometry, but in general relativity as a whole. With this tensor, we can find the paths that object will travel in a black hole, which is called, like, we can find the paths that objects will travel, like when they're orbiting black holes, when they're falling into black holes, and we can actually it has been calculated. We can actually calculate what that would be, and we will actually calculate what that would be in a future video. But the metric tensor is really important. So some people would say that it is your space, or it defines your space. I would say that's a stretch. In my personal opinion, that's quite of a stretch saying that, because I would say that, like, your space is independent of your metric tensor, because some spaces don't even have a metric tensor. I would say that your space determines your metric tensor, and from there you can find out stuff in your space, because space is real. This math isn't real, quote unquote. So the metric tensor will describe your space, and it's going to describe everything else. So it's really important in the subject. I cannot emphasize that enough. Your metric tensor is really important in the subject. We'll be studying this a lot, okay? And for our last thing, not last, second to last thing, what is this? Well, what is this over here? This gamma thing. What is this symbol that we see in the equation? Well, it's called the cosmological constant. See that 10 times fast for me. Basically, Einstein, when he first derived his equations in B. out Hilbert, Einstein discovered that, hey, when my equations actually predict that space is expanding, how can that be? Space obviously cannot expand. Space obviously must be static. So let me put this constant that would correct these equations so that space is static. So Einstein derived his equation, and he basically just found out that his equation predicts that space expands, and he was like, space doesn't expand, what? So Einstein put this constant to correct for that expansion, and that was wrong. This constant doesn't actually exist. Einstein just put it there to make his math work out, which is such a classic physics move. When your calculations don't add up, you just put a mystery dark number. Like, if you find that 1 plus 1 equals 3, you just put a magic number to make your math work out. It's a meme in the physics community. So before I start going off and rambling, this constant Einstein just put up to make space be static, because when you actually solve for your metric tensor, you find that it depends on time. So as time goes on, your metric changes, which means that the distances between 2 points will actually change over time, which means that space is expanding. And the first person to recognize Einstein's error was George Lemaitre. He was this Catholic guy. I think Roman Catholic, I'm not sure. I don't know about his origin, but Georges Lemaitre I'm not sure how it's spelled or something. He was a physicist or mathematician. He was also a Catholic priest, and he discovered that Einstein was wrong in adding this constant. He realized that his equations were actually correct in their first form. Like, they tell you, don't change your answer. Your first answer is probably correct, and in this case, it was correct, or almost correct, as we'll see later. So Georges Lemaitre find out that he said, "Hey Einstein, you're wrong. Turns out the space is expanding, and if you rewind back the clock, you find out that all of space was once a small point in that space." Well, that doesn't make any sense. But he found out that if you rewind back the clock, all of space was compacted into like kind of one point ish. So that's just the Big Bang, space expanding. So he discovered the Big Bang by just showing that Einstein's first equation form was correct. If Einstein would have just realized that he shouldn't have added that constant, he would be credited with discovering the Big Bang, which would probably hand him another Nobel Prize. I'm not sure if Lemaitre got the prize for his discovery ish, but at least, and I know that he should have gotten the prize. And the Big Bang was later proven to be correct and stuff. Blah blah blah. I don't want to go off on a tangent, but yeah, that's the story of the Big Bang. So that's the constant. Our last tensor that we're going to deal with is called the stress energy tensor. And that deals with the energy density of your space. It says that, hey, if I have some energy in some space, the energy is gonna it just tells you the energy in a space. This tensor over here, this stress energy tensor, just tells you the energy of the energy of your space. Okay? And it's actually not a true tensor. It's called a pseudo tensor. Why is it not a real tensor? Because a tensor must be invariant under all coordinate transformations. This tensor over here is only invariant in some coordinate transformations, but not in all of them. So it looks like a tensor in some transformations, but not in all of them. This is due to the math of special relativity, which we will talk about in the future. But that's the gist of it. And now we've discussed every part of this equation over here. Let's just recap what all of this means, okay? Let's recap what all of it means. It means this. I put a lot of drawing. Okay, I made a mistake in writing so many things over here. Oh my gosh. Okay, let's recap. All these elements on the left side of the equation tell you about the curvature of your space. Like here we have a Ricci. Oh my gosh, I forgot to talk about what this is over here. This right here is called the Ricci scalar curvature. I totally forgot about it because there's so many R's in this equation. So there's so many R's in different geometry as a whole. This R over here is a Ricci scalar curvature. It just says that if I have a plane, the volume formula is blah blah blah. If my plane is curved, if it's a curved space, then my volume changes. It basically says that when space is curved, the volume of an area will go up, which means that I can have a bigger volume on the inside than what's on the outside for a curved space. That's what it basically says. Okay, I wish I could talk about that more, but that would kind of ruin what I just built up. So sorry about that. I'll talk about that in the next 27 videos. So all of these elements over here, they all describe the curvature of your space. And this over here describes the energy of your space, right? So when your energy is positive, your curvature must be positive. When your energy is 0, your curvature must be 0. So we can actually group this whole chunk of this equation. We can just group it into one tensor, one big tensor called the Einstein tensor. So poetic, right? And we can just call this ugly mess, we'll call it a constant k. And we can say that the Einstein tensor equals k times the stress energy tensor. And that is the most simple form of the Einstein something. So I could be even more mad lad and just call this a whole new tensor, but let's just keep it like that. So this describes your curvature of your space. This describes the energy of your space. This literally tells you that when you have energy in your space, you have curvature. So when there's energy in the space, that will curve space. That will curve space time, and which will cause objects to fall down because time is curved. That makes no sense, and it sounds like I'm on LSD or something. Like time is curved. Like, oh, that's stupid. I know, but it's physics. All of it is stupid. So that's what this whole thing is telling you. When you have energy, you have curvature. Because when there's no curvature, the Ricci scalar and the Ricci curvature tensor would be 0. This whole part would be 0 if there's no curvature, and this would be 0 as well. So yeah, when there's energy in space time, then your space time would be curved. Or the famous saying, matter tells space how to curve, and space tells matter how to move. And for our last remark, we'll talk about what space-time actually is. What is space-time for the last part of this video? Well, you're actually familiar with space-time, but just in a different way. Space-time is the 3 axes of space, okay, plus 1 dimension of time. Another dimension of time. So think of this arrow like pointing at you on your screen. That would be so cool if that could happen. But basically, in space-time is just your 3 dimensions of space, and then 1 dimension of time. Or if you want to be like 1D-ish, you could just say that space-time is just the x dimension plus the time dimension. It's just a graph. Not a graph, but like, we call this depiction called Minkowski space-time, or aka a space-time diagram. And space actually, we can describe space with this space-time diagram. Like, in the space-time diagram, you have the 3 dimensions of space, x, y, and z. Then you have another dimension of time, like another time dimension. And we tend to simplify this drawing with just t and x. Okay. So if an object is over here and it's not moving, it's moving through time. And if there's some gravity, like if there's some black hole or something cool like that, if there's a black hole that's really dense, almost as dense as you, that was a terrible roast. But if you have a black hole and you have a point over here, turns out that the path through space-time would be curved. So this path would look like this over here. So you can see how time is being curved and how space is being curved as well in this depiction. Now that's really simplified. There's a whole thing called 4 vectors and 4 momentum and 4 velocity, and Lorentz transformations, and past and future light cones and stuff like that. Where like your future is blah blah blah. We're gonna talk about that in the future. That's actually pretty clever in the future, but that's pretty much what it is. Okay, so sums up this video. We learned it. What did we learn? What did we learn? Well, we learned three things. We learned about the Einstein field equations. We learned about what space-time is, and we learned about the equation. We learned about the. We also learned about the universal equation. Now, what is the universal equation? I actually haven't explained that yet. Well, the universal equation is an equation that describes everything in the universe. It just unifies everything in the universe. And universal equation is what Einstein worked on his last years of his life. And it has been unknown for centuries until now. I will write out the universal equation right now. The universal equation is K equals